Alright, in this problem there is a wire which is connected to by a spring into a support. Say this is a wall, and this wire has a current I, and this is actually inside a magnetic field which is basically into the screen, out of the screen, direction of the magnetic field over here. And due to that current, is said that is create a force on that wire. We know that due to that force, this spring is going to be extended 1 centimeter when the current passes through that wire. Now the question is, how big is that current? Fine. To solve this problem over here, this is actually the concept we are going to use, that the force on a wire, which is basically, I'm writing that magnetic force, which would be I into L cross B, right? This is to be the force, and the magnitude of this force, we can write this force of this magnitude I L B sine theta, where theta is the angle between L and the B. If you think about the L is the length of this one, which is towards that direction, downward direction. So if you consider, so this is actually that length of this wire, and the magnetic field actually that out of the screen, right? This is the case. Then the angle between these two vectors actually is 90 degree, right? I can draw in that form. So this is your length, which is the downward, and this is actually your magnetic field, which is out of the screen. The angle between these two vectors actually the 90 degree. Then we can say that magnitude of this force, which would be that I L B, right? Since theta actually that 90 degree. Fine. Then what would be the direction of this force? I have to find out that one first. How am I going to find out? We can use that axis over here, or I can use the right hand rule in both the case, right? I'll put my index finger into the first vector, so that's mean towards the length, right? This is the case. And if you rotate, then you will find out the direction of that force. Since this spring is going to be that compressed, it means that the force on that wire, it be towards that direction, right? So this is basically the direction of this magnetic force over here. You can also use the right hand rule. I'll put my thumb to I'll put my index finger. Say if I use the different color, so I'll put my index finger towards the downward direction, and if I keep my palm towards the second vector, that means towards the magnetic field, which is in this case actually out of the screen. Then if I rotate my rest of the finger towards that screen, so that means towards the second vector, then my thumb would be basically towards that left hand side, which would be direction of the magnetic field. I can also use that mathematically, that the direction of the magnetic field be towards that direction. For that one, say I'm going to choose, say this is my x-axis, so I should say this is the I head, this is that j head, and say the k head is out of that screen. Then I can also find out, say that L, in that case I should write L is basically that minus L J hat, and the magnetic field B is, say that the magnitude of B and positive K hat, right? Now I'm going to find out, look at this, the direction of FM would be that I into L. I should write the L is minus L J hat, cross B is B K hat, right? Then I can write down this FM would be minus I L B into J cross K. Now I'm going to use that properties of the univector vector I J K. This is J cross K. I'm moving to the counterclockwise, then you see that K hat J cross K would be basically that positive I hat, right? Then I'll find out A from M. The magnetic force is going to minus I L B I hat, which is towards that negative X direction, right? Towards the leftward. Mathematically I can also find it. Fine. So when this magnetic force is going to apply onto that wire, the wire is going to be that moving towards the leftward. It means that the spring is going to be the compress. These two spring will be the compress. Then the elastic force on the spring would be provided by elastic force on the spring 1 plus that elastic force on the spring 2, and this total elastic force on that wire or the spring would be basically towards that direction. So this would be that direction of this spring force, right? Then I can write down, since the spring constant has the same, these two are identical spring. The spring has a spring constant. Then I can write is going to be basically Kx plus Kx, which is give me actually that 2Kx, right? If you express in terms of vector, I can say this Fs would be 2Kx positive I hat. Now these two forces must be going to be basically that equal, right? So now we can say this Fm must be equal to this Fs. Now Fm, actually I take the magnitude basically over here, I L B, because I can write down the net force of this case actually 0. ILB must be actually 2Kx, right? Then I can find out that I from there is going to be the 2Kx divided by L into B. I know that everything, right? So which the K is that basically that 10 Newton per meter. That's give me the spring constant of this spring, and it's compressed that 1 centimeter. I have to convert that into meter. 1 into 10 to the 1 into 10 to the minus 2 divided by length, which should be, now the length of this wire would be basically length of this magnetic field, because this is actually that effective length, that one, right, which is actually the length of this magnetic field region. Although the length of the wire is not given, we can consider this will be the effective length of that wire, which is actually that 20 centimeter. So now I can use, it would be that length would be 20 into 10 to the minus 2, and the magnetic field is given actually that, what is that? It's a 0.5 Tesla. So I should write it's a 0.5 5. And if you solve, you will find out that current into that wire would be that 2 ampere. So this is would be that current into that wire. Due to that 2 ampere current, the spring is going to be compressed 1 centimeter. Both two spring actually going to be compressed towards negative x direction. That means that leftward due to this 2 ampere current into that wire. This is the answer of this question. Okay, thank you very much.